Hello, everyone. Today we have Kaichun Mo at our MLFL talk. Kaichun Mo is a sixth year and final year PhD student in computer science at Stanford University. And he's advised by Professor Yogi Bas. Before that, he received his BSc degree from the ACM honored class at Shanghai Jiao Tong University. His research interests focus on understanding 3D shape structure and semantics for various applications in 3D vision, graphics, and robotic manipulation. He has interned at Adobe Research, Autodesk Research AI Lab, Facebook AI Research, and he has published papers at various conferences such as CVPR, ICCV, ECCV, NeurIPS, ICLR, SIGGRAPH Asia, AAAI, and CORL. I will let Kaichun talk about his awesome work.
Yeah, thanks for the introduction, Gopal, and thanks for inviting me. And also thanks Kalpesh for organizing all of this. Yeah, so today I'm very happy to be invited by the UMass friends to talk about some of my research in my PhD. So the topic is on learning 3D shape structure and semantics. And my research focus, as introduced by Gopal, is on 3D vision, graphics, and robotics. So basically the core is to understand, to use deep learning to learn some representation for 3D shapes. So particular for expressing the 3D shape structure and semantics. So I believe that understanding 3D shape structure and semantics is an important problem that lies at the intersection of vision, graphics, and robotics. So on the vision side, given a scene, a point cloud, or anything that you can scan, so the first job you need to do is probably to detect the object and segment the object out. And after you do that, depending on the different downstream tasks, you might also need to consider to reconstruct the shape. And once you have the shape, and if you want to do something upon it, like if you want to manipulate it or understand it better, you may also need to parse some semantics, its parts and its structures. And on the graphic side, so once you figure out like the shape grammar, so you can use that to synthesize novel shapes, to create new data content to be used in a VR setting or making movies. And also for in many of the computer-aided design software, you can imagine that you can load two models and try to interplay between them. So you want the interpolation to be smooth and structurally meaningful and reasonable. And also you may want to do some shape editing for your different downstream needs. And on the robotic front, so once we understand the shape, the semantics of that, we might need a robot agent to manipulate with it. For example, if you want to open the door for navigation. And for this task, you need to understand the affordance, like where you need to grasp the handle, and also the functionality of the door, that the door can be opened. And also there is the articulated part involved here, that the door can be rotated along a joint axis. And all of these are important factors to understand for a 3D shape. So you will see in today's talk, I will cover like two works as an example that will cover both the graphic side and also the robotic side. And the vision is at the intersection. Yeah, so there are plenty of tasks, and all of the tasks are quite challenging, like on understanding 3D shape. So on the left is more graphics, and on the right is more robotics. So yeah, so you might need to, like given some models, the first task you might need to consider to do is to segment it into the parts, because different parts have different semantics, and the structure entails some important properties. Like the four legs of the chair need to have the same length so that it can be functionally correct, so the people can sit on it. And once you figure out the parts, you might need to consider how can you use this part to recompose them together to make up some novel shape for the graphics application. And in the middle, I would say it's more vision. So you want to, given some image of the shape, you want to figure out its structure. So the structure is very important. It entails a lot of functionality and also the semantics of the shape. And some of the shapes have articulated parts, for example, the handle and also the switch. So these parts are really small, but they're really important for robotic applications. And you need to perceive, for the part segmentation for this articulated part, and also to figure out as motion type, is that a prismatic motion or a revolute joint? And you need to figure out the parameters for those. And on the right, so you might need to figure out some specific regions or parts to grasp semantically for a shape for different downstream tasks. And also for some of the shapes, understanding as object or part state is very important. So for example, for robot navigation, you need to open the door in order to go from one room to another room. So this is, of course, it's not an exhaustive list, but I just want to give you some feeling about the problem that I'm solving in my PhD. And you will see two concrete examples that try to solve. So one on the structure side and one on the semantic side. Yeah, so I joined Liu's lab 6 years ago, and there is a very good data set called ShapeNet. So it's a very important data set for 3D deep learning. So it's a large scale data set containing a lot of 3D models. I believe there are millions of models there, and they are well annotated for a small subset. So it's not really small, so it's also a large scale subset. It contains 55,000 models that are well annotated. And this data set have already successfully pushed the frontiers of the 3D deep learning for many applications in vision and graphics and robotics. So I joined the lab to add more annotations on top of ShapeNet. So the first I did is the part network. We try to annotate the fine-grained parts of the ShapeNet models. So for example, you can see the keys on the keyboards are all separated out and annotated, and all the buttons on this dishwasher and buttons on the microwave, and all the lamp parts are annotated out, and the handles of the mud, and the views for the display. So these parts are really small, but the reason that we focus on annotating them is that they are really important for a robot to interact with. So the parts are really small, but they are super important. And that leads to the next work is more on the simulation side. So we built up this Sapien physical simulator so this is the first time that we can bring the ShapeNet models, the large scale ShapeNet models into a simulator and to live together with a robot. So the robot can play with this diverse set of 3D shapes in order to try to learn how to accomplish diverse set of daily tasks in human environments. So this rework is basically the foundation for the works that I'm going to talk about today. And let me give you more details and look into this data set and simulator. So PartNet provides very fine-grained part annotation. As I said earlier, all the small parts but are crucial for interaction are annotated. So you can imagine there are a big annotation effort here, and also there are many ambiguity for definition of parts. So it's really hard to canonicalize the annotation. So different annotators will annotate parts in different way, in different granularity. So how do we annotate this data set to achieve a canonically consistent data set annotation? So the core idea is that, so we just employ some experts in shape design, and we found some common used tags, the names to describe the parts for a category of shapes. And we define this canonical template. And in this template, to cope with different granularity of the part segmentation, we just naturally introduce the hierarchical structure of it. So the first level annotate the coarsest parts definition, like the back and seat, head, arm, and the base and footrest for this chair. And you can imagine that you can further divide the chair back into some back support, some back surface and back frames. And you can further divide the back frame into some holistic frame or horizontal bar or vertical bar. So empirically, this template work well to explain maybe 95% of the shape. And for the other 5% of the shapes in the category, we also allow some freeform naming that if the annotator believe that they see a part that does not belong to any of this definition, they just add their own name. And on the right, I'm showing you one specific chair instance that can be well explained by this canonically defined template. And you can see that there are so many parts, and and the parts are segmented in different levels to encounter the for different needs for different applications. So if you don't really need to segment into the very detailed, like the primitive parts, then you may just stop at the first level. But if you do need, for example, if some of the leg is broken and you need to figure out it's broken and you need to fix it, then you really need the segmentation at a very fine-grained level. And this is the backbone of the structure I'm talking about in the scope of this presentation. So the structure basically composed of a hierarchical part tree and containing the parts defined at different levels. So by having this canonical template, the good thing is that we can explain two different chairs in the same manner so that we naturally induce some correspondence between them. For example, the sofa and this regular chair, so they are very different, but like the base are shared, the leg are shared. So the same color indicate that, so there is the correspondence, like the back are shared. So that this will be very useful that you can, if you are interested in figure out some correspondence, that will be very useful for interpolation if you want to interplay between these two shapes. So the other important factor that we want to add in the structural representation of shape is that we also want to introduce part relationships. Part relationships are also quite important. For example, the foreleg need to have the same length, and they need to support the chair in parallel, so that the chair will not fall if a person is sitting on it. So we add many relationships, and you can think of more. So here we are using the adjacency relationship, like the space is adjacent to seat and seat is adjacent to back. And also for describing the relationship between the legs, we have the symmetry relationship. So here there are three edges because there are three types of relationships, like the rotational symmetry, reflective symmetry, and translational symmetry. And these two legs satisfy all the three. So this gives you a complete picture about what do I mean by structure of a shape. So we are just using this hierarchical part structure, and also the rich part relationship between them. And this is what we call the structure in the context of this presentation. Yeah, so on the robotics end, if we can load all of the StructureNet models in a simulator and use a robot to interact with them, we can see that. So this video is it's done by human using a joystick. So this is the manual operation. So this is not an algorithm. So there is still a big gap that to achieve this by some autonomous agent. So this task seems very easy to you, but it's very difficult for AI because it involves many perception and robotic control and planning problems. So you need to figure out the button. So where is the button? You need to segment it out, and you need to understand like where is the handle of this door and what is the axis of this door, and where's the handle of the mug, and how do you grasp it and stably transfer it from one location to another, and how do you stably put it on the table. So there are so many perception problems and control and planning problems involved here. So that's also the motivation why we are building the simulator, that to study like the diverse robot object interaction tasks at a large scale, supported by the large scale StructureNet model repository. So the backbone of it is, again, the data set. We have a large scale annotated data set, the subset of StructureNet, and we annotate the parts and also the part articulation parameters. And we have already demonstrated that using Sapien can support you study many perception and robotics tasks. So for example, like in this video, I'm showing that you can use some heuristic-based algorithm to grasp, open the door or drawer for a big set of cabinets. So you no longer need to overfit your RL or something to one instance. And here it's showing reinforcement learning. So namely, I'm using a TD3 RL algorithm to learn how to open the door. So this video is trying to show you that we can use this physical simulator and also the large scale StructureNet models to backbone some study of perception and robotics tasks at a large scale. Yeah, so that's lay out some foundation of the data and the simulator. So let me go into the two papers that I'm planning to talk to you. So the first paper is more on the graphic side and also the studying the 3D shape structure. So I will talk about the structure network that using the hierarchical graph network to generate novel 3D shapes in a structure-aware and part-aware manner. And the second work will be more on the robotic side, is we are trying to develop a self-supervised learning framework that can automatically learn the affordance for the semantics of 3D shapes for a big set of 3D shapes, so that you can learn how to manipulate with the shapes. So the first work, StructureNet, is accepted as SIGGRAPH Asia 2019. And from the teaser, I want to give you a feeling that either from the source point cloud input with no part segmentation, or from an image, so you can first reconstruct the shape into part-aware and structure-centric representation for the shape, so that the different color indicate the different parts, and also like there are many edges drawing the connections between the parts. So that's the relationship that I talked about in the previous slides, so that you have some structured representation for the shape. And you can also get that from the image. And the good thing of getting the structure representation is that it allows more semantically reasonable interpolation between shapes with different structures, so that you can see that there are not only the continuous change for the geometry, but also the discrete structural change that is more semantically meaningful. So especially for interpolating between two shapes have different structures. So compared to generating the shape in a holistic manner, of course, if you generate them in a part-by-part manner, the parts naturally come with labels, and the labels will be useful for downstream tasks. And also, if you generate the shape part by part, so the part boundaries will be sharper, and also you naturally have some structure for this shape and relationship between the parts. So, for example, the four legs has to have the same length, and they are symmetric. So all of these informations are really making this structure-aware shape generation something important. So the overall architecture for the framework is actually quite easy. It's just a variational autoencoder. We have the encoder and decoder, and in the bottleneck, we try to make sure this is very close to a uniform Gaussian, so that in the test time that you can just sample random noise and you can decode to generate the shape. So the tricky part here is that we are encoding and decoding a very irregular structure representation of the shape, which is essentially the structure tree that I show you before. Like for each shape, we are representing it as a part hierarchy, and there are also rich part relationship between the sibling parts. So how do we design the architecture to encode this type of irregular format of data, and how to decode it? So it becomes the central problem in this work. So let me walk you through in detail how do we do this. So the encoder and decoder are both recursive neural networks. So if some of the audience are familiar to are working in NLP, so you may be familiar with this tree LSTM idea. So basically, we parse the language into a tree, and we can recursively encode the language and recursively decode. So we are using the very similar idea here, but processing the tree for 3D shape data. So for the encoder is it proceed in a bottom-up manner. So starting from the leaf node part geometry. So here I'm showing you the example of using bounding box to represent the part geometry. So it also works if you want to use the mesh to represent the part geometry, or if you want to use a point cloud to represent it. So yeah, you just have different encoder and decoder for the part geometry, and that the same framework should also work. So given this leaf level parts, so the first task is to the first layer is to use a geometric encoder to encode each of them into a feature, and you form some graph here. So here is for all the children nodes belong to the same parent, they are grouped together, and then we employ a graph encoder to extract the parent node feature by just performing some symmetric operation like a max pooling or average pooling over the sibling, the children nodes. So this will be ignorant to different numbers of children nodes for parents. And we just apply the same graph encoder recursively until we reach the root node. And here I'm omitting the edges. So the edges here, are just like the adjacent relationship and also the symmetric relationships are just play as the role as the edges in these graphs. So that's why we call this to be a hierarchical graph network, because it's a hierarchy and we have the local graph between the sibling, the children nodes. And we just use this part relationship, we encode and decode them as the edges in these graphs. And the decoding process is the reverse procedure that starting from the root node, we recursively decode the entire tree in a top-down manner. So first we employ a graph decoder that decode the 3 nodes and also the 2 edges between them. Yeah, remember that we are using a VAE, so we know that the ground truth tree, and we have the input, so we are matching the output to the input. So one tricky point is that we don't know how many children nodes for each parent. So what we are doing here is we just assume that there is a maximum of 10 parts per parent, and we just decode, we always decode 10 nodes. And because we have the input tree to regress to, we use some matching algorithm to match all the 10 prediction part to the 3 ground truths and pick 3 out of the 10 and train the 3 to regress to the 3 ground truths. And we will train the other 7 to vanish. So we will also predicting an existence score for each part. And if at the test time, if the existence score is below 0.5, then that means that part does not exist. So we always decode 10, and we train 3 of them matched to the ground truth to regress to the geometry, the geometry of the 3 nodes, and we train the other 7 to vanish by training an existence score to below 0.5. And for the edge decoding, we just decode the edges like among the nodes, and that is the very simple classification problem that you just classify whether you have an edge and what is the type for the edge between two nodes. And we can just recursively apply the same graph decoder until we reach the leaf node. And at the leaf node, we can just use a geometry decoder to decode back the part level geometry. So again, the geometry, so I'm here showing a bounding box representation for the geometry, but you can also replace it with the mesh or a deep SDF or some mesh or point cloud representation for voxels. So here I'm showing some result. On the left is the box result, and on the right is the point cloud result. And you can see that we can generate. So we are actually generated the parts. We are actually generated shapes with parts with labels and also with structures. And also each part is generated independently, so that so there's a clearer structure and part boundary between the parts. And in a follow-up work, we try to expand it to improve it to generate better results. As you can see here, we are using a mesh, and you can see the mesh is really of high quality, and also some of the local details of very small parts that are generated well, because we are generating the parts one by one, so that there is the equal attention for each part, no matter what is the size for the part. So for small parts, sometimes they're really important. So we need to give them the same treatment as the other parts. So having this structure also give us also enable us to accomplish some part level interpolation. So which is something that you cannot achieve if you train a holistic shape generator. So here I'm showing you an example. So there is a shape on the left and another shape on the right. They are quite different. And there are two rows of interpolation. In the first row, we are interpolating the backrest only. Because the two chairs are explained by the same template, and we have the correspondence between the parts. So what we do is we just interpolate the subtree for the back, and we just maintain the same tree node for the base. So the base is using the base of the left shape, and for the back, we are interpolating the back style from the left one to the right one. And what is interesting is that you can see, so the base remain almost the same, but not exactly the same, because we need, so while interpolating the back, we need to make sure that the intermingled shape of the back and seat, they come together to form a realistic shape. So maybe that will be more clear if you look at the second row. So then in the second row, we are interpolating the base while using the style of the back of the left chair. And here you are seeing that, so the base of this shape is quite far from the style of this sofa, because the sofa have a very short leg, and here the legs are pretty long. So the reason is that to be compatible with the style of the back of this left chair, we need to make sure that the shape is realistic, so that we need to adjust the base style accordingly. So we cannot just brute forcefully combine the base of this, copy the base of this chair, and copy the back of the left chair and put them together, because they will not form a realistic shape. So we are optimizing on a manifold of the realistic shape structure and the geometry. So we need to come up, reach a balance between the back and seat. So that's something really interesting here. Yeah, so we can also, so having this structure description also allow us to do many other applications. So here I'm showing an example that we can disentangle the geometry and structure of the shape as much as possible. So for the two given input shape, one at the top left and one at the bottom right. So the x-axis is interpolating the structure of the shape while keeping the geometry as the same as possible, while the y-axis is interpolating the geometry counterpart. So you can see that for each column, the structure are the same and the geometry are slightly changing. And also for if you look at each row, the structure is changing and the geometry is more or less in a similar style. And in another ECCV work, I showed that we can do some conditional generation. So imagine that you are having some sentence from the user that describe a shape that you want to make. So you can parse that into a tree, like the structure, the ParNet tree. So this is just a semantic tree without any geometry attached. So the task we want to do is to generate a diverse set of shapes that satisfy the structure of this or the sentence that the user provides. Yeah, so we see that all the generated shapes, they satisfy the same structure, and there are some slightly different changing for so there are some geometry variation in the generation. Yeah, so in another work, we can also allow some structure and part-aware shape editing. So given two shapes, so you can extract the difference between the two shapes. Like here, we are basically removing all the bars and just replace a simple trunk for the back. And we can, given a second shape, and we can transfer the same edit and generate the edited shape the output for that. And also, given a source shape input, we can generate different modifications in the local neighborhood of the shape. So this will be very useful for some shape editing applications that you want to create the new models by slightly changing some of the parts and some of the structure with some of this geometry. So there are two rows of generation result. So one is interplay, one is slightly changing the structure, and one is slightly changing the geometry. So it's the same. So for the structural variation, we keep the geometry as same as possible, and for the geometric variation, we keep the structure as the same to the source shape as possible. Yeah. So I want to briefly talk about another two interesting works that related to 3D parts. That's more on the I would say on the reasoning and side and the learning side more than the graphics applications, and that can transit the topic well from the graphics end to the robotics end a little bit. Like, so the task we want to do is to assemble a shape from parts. So imagine that you bought some chair from IKEA. Then, so before you open the box, so you'll see an image on the box that of an assembled chair, but after you open the box, so you will see only these parts. So the parts are very similar, like you have no idea how to assemble them if you don't read the menu. So the task we are trying to address here is to, like, given a single image and some parts, and how do we assemble the shape back? And in another work, we try to remove the image constraint, and given the part, we just want to generate the shapes that using this part to generate realistic chairs. So I would say for the project on the left, so it's more for robotic application that we want to really assemble an IKEA chair according to the image instruction, if you do not want to read the menu. And on the right, it's more like on the graphics applications that given some parts, so you want to design novel shapes. So it's more from the company side, like given the part in their part repository, how many novel shapes, how many new products they can design in order to give to the user. So a very quick introduction for the method. So basically, we are using this graph neural network iteratively. And so given the parts, so we figure out this pose, we draw some edges among them and try to predict the pose at the first round. And we pass the temporary assembly into the second round, and to do another round of reasoning, the geometric reasoning between the neighboring parts. and the related parts. And then we can figure out the second round of post hypothesis, and we do that for multiple rounds. And here shows your probably better some example in action that given the first step, it will try to make sure some the big part like the back, seat, and legs, they are placed at the place. Well, the other parts is very difficult. It's got quite confused. What are these parts and how to use them? But once the sketch of the shape is clear, they can try to start to put the parts, the other small parts in position. Like they can try to add back. So that's what I mean by the geometric reasoning. So you need to reason what's the semantics for the parts and what's the functionality for the parts, and how do I make sure that all of the parts come along with well with each other to assemble a functionally realistic shape in the end. So I don't have too much time to talk about this in detail, so please refer to the paper if you are interested in this. So I think this is a really challenging task. Some of the extension would be like how so you should read manuals, right? and look at some examples and how can you leverage the signals like the realistic shape manifold, so all of the both works are trained in a supervised manner. So you can easily imagine that if you can have train again style network, that you can remove the supervision. Yeah, there are many limitations for the works that I have introduced to you in previous slides. We are using the heavily annotated ParNet dataset. So without this dataset, we cannot define the canonical structure, the parts and the part correspondence, part semantics, the relationships. So all of these are annotated by human, and it's very, very heavy. Yeah, but the good thing is that there are some recent work try to emerge some canonical part hierarchy in an unsupervised manner. So if you are interested, go to look at those papers that are really showing some appealing results. And also we are training a network per category because we need to rely on this canonically defined template per category. And also the training is pretty heavy. So the difficulty I encountered is that the different shape has different structure. So I can't even use GPU to parallelize the training. So I'm actually using some high-end CPUs to train the network. So there are many things to improve. So that's the first part of my talk. And for the, yeah, so if there's no quick question, maybe, yeah, I should move on to the second part. Yeah, so as I introduced before, there are like the very diverse set of 3D geometry, and the parts have different functionality. And on the right side, we want to finally ask our robot friends to do many tasks for us by interacting with this diverse set of geometry. And this is not happening soon because there are many challenges in between, and how to bridge the perception interaction gap is an ongoing research direction. So the difficulty mainly lies on the unstructuredness of the environment and the diversity of the 3D shapes. And there are many perception and robotic controller and the planning difficulties. So I try to ask this question to myself. So what are the good visual representation for robots to manipulate over a big set of 3D shapes? So we need some sort of abstraction, some representation. So in order to make the learned downstream policy to be generalized to different novel task time instance, or even we want to generalize the skill to some novel categories that we have never seen during training. So there are many options. So computer vision progress very fast. So there are many like pose detection, key points representations, so the bounding box structure representation, some skeleton representations, or you can use the StructureNet type of the part aware, structure aware reconstruction for the shape. So I would say they are all correct answer, but I would say it's not perfect because they are task agnostic. So being task agnostic gives the problem that they may be insufficient or unnecessary. So for example, if you want to do the task of grasping, then using this bounding box abstraction may be not enough. So you need to know the detailed geometry of the shape. But on the other hand, if you only want to grasp like the back of the chair, you might not need to have the detailed reconstruction for the legs. Right? So there are different needs for different applications, and we probably need to define task-aware representation for different tasks. And so today I will give you 3 examples. I will focus on one and briefly talk about the other 2. So basically, I'm trying to learn some affordance that can hopefully generalize across a large-scale set of shapes. So so the Where to Act work is accepted at ICCV this year, and is a collaboration with the Facebook AI Lab. So what we are learning here is we are learning some task-aware affordance, and the affordance is also task-aware. So given this cabinet, so we want to study where you can push. So more red means that you can push at that point. And you will learn a totally different affordance for pulling tasks. So basically for pushing, it highlights all the pixels on the flat surface. Some interesting scenario is that if the flat surface is too close to some handle, then it's less likely to be pushable because there will be some invalid collision between the gripper to the handle geometry. And for the pulling affordance, so as you expected, you can see that this high curvature area, not only the handle of the drawer and door, but also the side of the drawers are also highlighted. So an interesting thing to notice that is here is really blue, indicating that this cannot be interacted. So this is again because the invalid collision between the gripper and the geometry of the door that will invalidate, like you can grasp the drawer at the bottom, this part of the edge. And then for each part, for each point that we predict to be actionable, we then predict how to action on top of that. So we propose a diverse set of gripper orientations that can successfully push or pull at the predicted pixels. And the result generalized somewhat to some real scans and real images. So if the texture are not, the texture domain gap are not too big, and also the scan pattern, the artifacts are not too big. So you can see that the learned information are quite local. So they are trying to pick up some local geometric properties for each task. So you can also train another network for another type of interaction. For example, for rotation, for scratching. So you just train the same framework, but for the other task. So how do we, so some of the motivation for the task. So given this cabinet, so you can do a lot of things, like you can pull open the door by grasping the handle, you can push the door to close it, or you can further open the door by grasping the edge and pull it outward. And there are 3 parts in each of the action items you can do: the what, where, and how. So what means what is the action type that you are doing. So you are pulling or you're pushing. And where indicate like the where to act, like the points. So where you should apply the action. And outward, so the how question basically is the more on the agent side. So what is the trajectory or the agent orientation that I should use in order to successfully interact at that pixel. So for the what, we just predefine some action skills, some action primitives like pushing or pulling, and we are training different networks for different types because we consider them to be different tasks. And for the where question, we just predict this per pixel then heat map to indicate the actionability at each point. And for the actionable point, we further predict how do we do the interaction? By propose a set of diverse orientations of the gripper. And each proposal is associated with a score so that we can use this score to rank and pick the one that we like. So the reason that we can train this for a novel task is that none of this require annotation. So we only require like the PartNet annotations. Like we have a lot of shapes and we know the parts and we know the part kinematic structure, like the joint axis. So we only need to know them. And we can just load the models into the physical simulator. And then there's no additional supervision. So we don't need any human annotation for the affordance. Also, we don't need human demonstration for the affordance learning. So all we need is to perform some simulated interaction by doing some self-supervised trial and errors in the simulator. So we can just randomly pick a point on the geometry, randomly sample an orientation for the gripper, and we can just do some short-term hand engineered trajectory and try to observe the outcome, whether that will move the part or not. So in the context of the where to act work, we only consider a short-term task, like by moving some parts surpassing the threshold of 0.01. So we try to break this assumption in the follow-up work. So yeah, let me walk you through the network. So our system can take either a 2D image or a 3D partial point cloud as the input. And we employ the 2D UNet or 3D PointNet++ to get a per pixel or per point feature. And then we have 3 decoding branches. So the first branch decodes the actionability score for each point or pixel. So it's a scalar between 0 to 1. Is answer the question, is this point actionable or not for this given task? And the second branch is the action proposal branch, is a conditional generative model. Like by feeding different Z, you will get some different proposals for different orientation for the grippers. And the final action scoring branch will take as input the proposed action, the gripper orientation, and try to associate it with a score. So you can see that the actionability scoring branch answer the where question, and the action proposal branch give the diverse set of proposals, and the action scoring branch give you the scores. So in the testing time, we just do this in this way. But actually in the training time, we are training in the inverse way. So we can directly use the simulated interaction to and use the binary cross entropy loss to train the action scoring module directly. So remember what we can get from the simulated interaction. We just randomly sample a shape, randomly pick a point, randomly sample an orientation for the gripper, which is the additional input to this branch, the R. And we directly observe the outcome of the interaction that can be used to directly supervise this score. And this is just a simple binary cross entropy loss training. And we found it's really important to train this module to convert first before starting to train for the other 2 modules. So for the action proposal module, it's basically a conditional generative framework. So we are using min of n formulation that we predict 100 predictions and make sure that at least one of them will cover the ground truth sample. So there could be other options like the conditional VAE or conditional again. So in one of my latest work, we see that the CVAE actually perform much better than using this min of n strategy. And what is more tricky is how to train this actionability score. So the actionability score, we have no direct supervision to train it because we probably need to sample very densely at all the orientation of the gripper. So if one of them succeeds, then that pixel is interactable, right? But we cannot afford to very densely sample all the orientations for the grippers. And for some of the points with some very subtle geometric context, so it's only a very small solid angle of interaction orientation can successfully interact at a pixel. So it's really difficult to sample some successful interaction by using randomization. So what we are doing is here we resort to a poor man solution. So basically we just leverage the other two decoder branch. So we ask the action proposal branch to propose, say, 100 proposals, and hopefully it's good enough to propose within that solid angle. And then we use this action scoring module to rate a score for each of the action proposal. Then we just compute the average score and we use the average to train it. So it's by no means the unbiased estimation, but empirically it gives you some good results, like I showed in the teaser image. So the score will approach to 0 when there's no successful proposal. So in that case, the action proposal network just propose random ones, but the action scoring module will always associate a very small score to it. And then by computing the average, the score will approach 0. And if that pixel is interactable by some action, hopefully the action proposal can propose it, and then it will be given a big score for that action, and then it will approach to 1. So empirically, we found that the system worked well to give you some informative affordance by using this poor man solution for the supervision. So I probably need to go faster. So another issue is by using this randomization strategy to collect data is will give you the problem of so it's really difficult to collect positive data. And if you only have very few positive data, then there are some severe overfitting issues. So for pooling only 1% of the random interaction success, and for the other task, you can imagine it might drop below 1% or 0.1%. Then you need to sample so much data in order to get enough positive data for the training. So what we are doing is we introduce some important sampling, like the online data sampling. So during training the model, we try to sample at the pixels that are predicted to be more likely to be successful, and we just intentionally sample more at those pixels just to get rid of the overfitting problem. Yeah, some of the results. So the network learns localize the geometric features. So that's the crucial point, so that it can generalize to novel instance and even novel categories. Because the information learned are quite local, so it give the foundation for generalization to some novel categories, even though you have never seen that category during training. So some interesting results. So the pixels more further from the axis are more likely to be pushed to close the door. And also if you pull up, so you should use the bottom pixels instead of the top ones. And the action proposal module can give you diverse proposals. So we are using a flying gripper here. We abstract away the robot arms because we want to make this the object-centric model, which is some property for the shape. And we hope to propose a diverse set of proposals so that no matter what is your downstream application, your specific robot arm kinematics, so maybe this trained model will always be useful for you, so that you can pick a subset that is applicable to your robot. So again, we are trying to learn some object-centric priors. So that's why we want to abstract away the agent side, the robot configurations. So in a follow-up work, we try to extend it to learn for long-term tasks and trajectories. So given the same cabinet, but here we are asking for opening the door for 30°. So besides predicting the affordance map, so of course the affordance map will be different from the where to act one, because only this point can finish task. So in addition, we also predict some trajectories and also the orientation for the grippers. And so we predict the trajectory in terms of the free-form trajectory, we just specify 5 waypoints. So for each waypoint, there is the position that you need to reach and also the orientation for the gripper. And we just predict 5 sets of poses. And that will give you a free-form trajectory. So again, we aim for a diverse set of proposal because we are using flying gripper and we want to do the task on the object-centric way. And for your different downstream application and robot configuration, you can just pick the one that is suitable for your task and setting. And it can also, the same self-supervised affordances learning framework can also be used to learn the object and object interaction. So given this bucket and this cabinet, so we can predict like where you can fit this bucket in the cabinet. So from this affordance prediction, you can immediately rule out the second shelf because if the gap is too narrow to fit the bucket. And among the other 3, you probably pick the bottom one because that is most likely to successful accomplish the task that you place it inside and you can close the door. So check this paper for more detail if you are interested in this. So the previous 3 work can generalize to real world to some extent because the learned feature is quite local. That's the reason it can generalize. So of course, if we found that it generalized less well to real images because the textures in ShapeNet are really not that realistic. And then, and of course, there will be domain gaps. But if you operate on the 3D partial scans, it works to some degree. And we also tried a framework on real robots. So we propose a trajectory and you can drive the real robot to follow the freeform trajectory in order to accomplish a task. Yeah, so there are some limitations. The biggest one is we are not having realistic physics parameters annotated in PartNet. So we are just using some domain randomization technique that we randomly sample like the. So actually, in most of the 3 works, we are just using set random physical parameters. So there will be some sync real gaps in terms of the physics or dynamics. And we are taking the single frame as the input, which give us some intrinsic ambiguity. For example, you don't know whether you open the door from the left or the right if there is no clear handle. And also for this case, you don't know whether the door is designed to be pushed inward or pulled outward. So in this case, we just predict that both could happen. And also, as I mentioned before, we are using the random strategy to collect data, and this may require really large-scale data collection. So if you think the CPU times are quite cheap, then this is not a problem because we don't need human in the loop. So we don't need human to demonstrate, human to annotate. You just maybe launch 1,000 CPUs to collect like hundreds of millions of so maybe hundreds of thousands of interaction trials, and then you can do it. But it really become a bottleneck for some of the tasks. So imagine if you want to use some robot actuator with higher degree of freedom, like the parameter space for the robot is get larger, or if you are using multiple hands, and that the random data collection strategy will like blow up, and so it will not scaling very well. Yeah, and that's it. So that concludes my talk. I basically cover like how to learn 3D shape, structure, and semantics, and I try to give you 2 examples: one for the graphics side, the generate shapes, and the other on the robotics side, and how to self-supervise learn the affordance for robot manipulation task. And thank you. I will take questions.
Thank you so much, Kaichun. Let's all unmute ourselves and thank Kaichun before we move to questions.
Thank you, Bob.
Okay, so we have some time left for questions. Anyone can feel free to unmute themselves or raise their hand, and then I can call out your name. Yeah, Sam.
Hello, Mo. Thanks for the talk, though. That's great work. So my name is Simon. I didn't quite get what happens when when you have a situation where you're not clear whether you should be uh, pushing the door, pulling it because there's no handle or something like that, and what's the failback plan for that? Because a human might just try all the possible options at that point, and then when one of them succeeds, then they stop. So I'm just wondering, what are the failback options in this case?
Yeah, so yeah, I'm not sure I understand the question, but if you're asking about like how, so why the affordance is important, like yeah, I think the affordance is trying to suggest some priors and how should you try to interact with the object if you want to open the door. And in the case that there's no handle, you just maybe like try to grasp the edge of the door, try to scratch the edge of the door and hope that you can open it. Is that answering your question, or I misunderstand?
Oh, kinda. So, in your design choices, how do you take care of that? So, you had previously shown that it will either look for a handle or not, and if it misses, it tries to grab. But I'm just wondering how, in the design choices for your architecture and thing, like how do you take care of that?
Yeah, so actually we do not explicitly model any semantic part in this work. So we do not. So the agent, so the network never know that this pixel is a handle or not. So it's just the geometry, like a point cloud or image, and treat all the points and pixels equally. So it doesn't know that that pixel belong to a handle. So I should look into that first. So it doesn't know this. And because we are using some random strategy to collect data, so sometimes it will try to grasp at the handle and see some success. So it will learn that that handle kind of geometry would work, but it doesn't have to learn that it's a handle because of it's a handle, so it works. And also, yeah, so the same framework treat all the other points so equally. So if it sees some other like subtle geometry can also be pulled to open the door, it might think that is also actionable. And also for the edges, yeah, because we are using the random strategy to collect data, so it can try everywhere on the part. And as long as that succeed finally, so that will be learned in affordance.
I see. Thank you.
Yeah, thanks for the question.
Okay, we have time for one more question. Anyone? Okay, great. I think people are leaving the questions for the one-to-one meetings in the afternoon. So yeah, let's just thank Kaichun once more. And yeah,
thanks a lot.
just stop the recording here.